Hello, everybody. It's Professor Monty. Today, what we're going to do is we're going to look at population proportions. So before, what we were doing was we were doing confidence intervals and hypothesis testing for the population mean. We're not looking at the mean or the average anymore. We're looking at the proportion of a population that has a characteristic. So remember, a proportion is, and I'm going to say it's a percentage, but I'm going to put percentage in quotation marks because the proportion is really a number between 0 and 1. It's a probability, but we often look at it as a percentage of the population. Wow, that wasn't good. Let's try to erase that. There we go. Erase those two while we're at it. So a proportion is a percentage of the population that has a certain characteristic. So for example, we may say something, and I'm just making these numbers up, 0.85 or 85% of the population of whatever group we're talking about here has brown eyes. Let's clean that up a little bit. So that would be an example, or maybe we'd say 0.12 or 12% of the population is left-handed. And so you can say any multiple of things. If you're looking at cars in the parking lot, you could say, oh, 23% of the cars in the parking lot, or 0.23, are black cars, something along those lines. So it's some characteristic. It's not a number that we're looking at. It's a characteristic. Do they have this characteristic or do they not? So that's what we're talking about here. So this is not numeric data. This is non-numeric data, or we often call it qualitative data. Okay, so that's the big change between the last several sections we've done and this chapter. This chapter is all about proportions. And so let me give you a little bit of notation. If we just use this curly letter P, they're not going to use a curly letter P. They're just going to use the letter P. If we say P, they're going to have that be for the population proportion. If we do P with a little hat over the top of it, that's the sample proportion, similar to X bar. So X bar was for the sample mean. It has a little symbol over the X to say it's coming from the sample. This has a little symbol, a little hat over the P to say it's coming from the sample as well. They even call this P hat. So when they refer to it, they'll say, oh, what's P hat? And then the formula for P hat is just X over N. And we know that if we're going to find the proportion of something, we would just say there's 12 out of 50. Well, we just put 12 divided by 50. So there's my formula where X equals the number in the sample with whatever characteristic we're looking for, with the characteristic. And then N is the same as it always is, sample size. Okay, so that's where we're going to start with, is we've got our population proportion. That's what we're going to be testing on, we're going to be saying, hey, is the population proportion this number? Well, we're going to use the sample proportion and probability to calculate the statistics to see how likely our population proportion is. So in our null hypothesis, instead of saying like mu equals 20, we might say p equals 0.3. Again, it's going to be a decimal number. It has to be a number between 0 and 1, or as a percentage between 0 and 100%. We typically put it a decimal number, so we'll go from there. In class, if you had put it as a percentage, I don't have a problem with that, but since we're filling it out online in the homework and on the test, we have to make sure we put it in the correct format that they're looking for. Okay, so let's go from there. In this section, remember it was called confidence intervals for one population proportion. And so what we need to do, let's set up the assumptions first. These are the things that have to be true in order to do these. The first one is that we have to have a simple random sample, or we have to have a random sample. Okay, so one assumption has to be a random sample. And the second, it has to be normally distributed. Or, as we saw before, a large sample. But large sample in this case isn't what it was before. It's not just that the sample size n has to be greater than or equal to 30. This time, it's a little bit different. The reason is if something happens either very rarely or very often. If I'm looking for somebody that has some rare blood disease and there's only 0.5% of the population that has it, well, if I only sample 30 people, chances are I'm not going to find anybody that has this rare disease. So in this case, what a large sample means, large sample for proportions, both n, which is, let's not say n, we'll get there in a sec. X, which is the number of people that have the characteristic, has to be, and I put in equals, greater than or equal to 5. So we have to have at least 5 people that have the characteristic. That's what we're going to determine is a large enough sample. And then n minus x, so that's the total sample size minus the people that have the characteristic. So n minus x is the people that don't have the characteristic. That has to be at least 5 people also. So you have to have at least 5 people have the characteristic and 5 people not have the characteristic. So if it's something around a probability of 0.5 that somebody's going to have this, we may be able to get away with a sample size of 10 as long as we have 5 have it and 5 don't. But if it's something extremely rare, then that x, to get x to be at least 5, you may have to have a very large sample. And if it's something that's very common, you have to have the n minus x, which is the people that don't have it, to be at least 5. So you may have to have a very large sample in that regard. All right, we will look at how to find sample sizes for certain things a little bit later, actually in this section. Okay. So let's go from there, and we're actually going to do one of these. Now, if you look in the book of this table, and we don't do any of that. For us, all we're going to do for confidence intervals, we just do them on the calculator. It's a one prop z interval. And so that's all we're going to do. Calculator, I'll show you how to do that in just a minute. But having said that, we are just going to jump in and do a problem. So we've got all the basics of what's going on. So let's go ahead and jump into one of these so that we see how this works. So I'm going to go in, I'm going to pull a problem out of the book. So let's see, it's problem 1250. So let me pull problem 1250 out of here. Here it is. I wonder if there's a better way to do this. Maybe I could have just copied it. So let's see. We're going to copy that. I don't want to be in there anymore. We'll get out of there. See if this will just go here. And let's move this up, and I'm going to paste it right about there. All right, so here's the problem. 1250 says life support. In 2005, the Terry Schiavo case focused national attention on the issue of withdrawal of life support from terminally ill patients or those in a vegetative state. A Harris poll of 1,010 U.S. adults was conducted by telephone on April 5th through 10th of 2005. Of those surveyed, 140 had experienced the death of at least one family member or close friend within the last 10 years who died after the removal of life support. Find and interpret a 90% confidence interval for the proportion of all U.S. adults who had experienced the death of at least one family member or close friend within the last 10 years after life support had been withdrawn. So let's pull a couple things out of here. First of all, is a Harris poll of 1,010. That is my sample size. So we had experience with the death. That's my X in this case. So we're going to go through and we're going to find a confidence interval. Remember, it says find a 90% confidence interval for the proportion of all U.S. adults who had experienced the death of at least one family member. So this 140 out of 1,010, obviously that's not all adults, it's a sample of them. We're going to use that sample to estimate the population proportion. So again, this isn't the average of something, it's a proportion. That's why up here we call it a one prop Z interval. Okay, the good news is they're all Z intervals. We don't have any one prop T intervals, so we don't have to worry about the distinction between T and Z in this case. Okay, so let's go ahead and do the problem. All we're going to do is we're going to go into the calculator and we're going to show you how to find this. So let's see. We've got the 1,010 and the 140. Let me just jot that down so I don't forget it as I'm talking out loud. So let's see. So we've got the 140, the 1,010. Okay. And we've got a 90% confidence interval. I'll jot that down as well. Okay, let's go to the calculator. I'll show you how easy this is to do on the calculator. All right, so we've got our calculator up. Just as usual, we're going to go stat, tests, and then one prop Z interval. Notice it's down here at 5. So I'll arrow down so that we all see it. It's right there. One prop, oops, that's one prop Z test. One prop Z interval, I guess it's down further. Let's keep going. There it is, one prop Z interval. It's at A, actually. Good thing I arrowed down instead of just hitting the number. So now I'll select that. And it says one prop Z interval. Notice if this says one prop Z test, you're in the wrong place. We will actually see that today. That's just in the next section. Okay, so the X value, that's how many people had the characteristic. And remember, it said that we have to have at least 5 people have the characteristic and at least 5 people don't to be large enough sample. Well, we have 140 that have the characteristic, so that's definitely big enough. And since our sample size was 1,010, all of those 1,010 except the 140 don't have the characteristic. So we have more than 5 that don't have the characteristic at all. That's why we're fine. And then it's a 90% confidence interval. So let's change that to a 90. And that's all we do. Calculate. We're going to get our answer. So there's our answer. I'm going to copy that down, 0.1207 and 0.1565. I'm not sure how many decimal places they want to go. But notice what they did. They calculated p-hat for us. This is the sample proportion. So about 13.9% of our sample had that characteristic. And then the confidence interval, we're going to start there. That's the middle of my confidence interval. And then we go to the left and the right, whatever the margin of error is. And that's how we got this 12.07% and 15.65%. So anyway, let's go enter those in onto our sheet. If we were doing the homework online, of course, we would enter them onto our online work. But let's just write this down. So our interval that we got, so it was a 1 prop z interval. And we got 0.12. I don't know why I asked how many decimals they go to, because we're not putting this in on the homework. And 0.1565. So we're going to word this. We can be 90% confident that the proportion of all US adults and then it's experience the death. I'm not going to write the whole thing. In the last 10 years. Was between 0.1207 and 0.1565. I personally like those better as percentages, so I would have liked to have said between 12.07, I'd probably go to 1 decimal place. I would have probably said between 12.1% and 15.7%. I would have probably said something like that. But since they said proportion, we leave it as proportions. If I just change that to percentage, then again, I would change it to percentage. Again, I don't know how they're going to ask on the online homework. Typically, they write this out and you just choose the correct one. And they wouldn't give you two. They wouldn't do it as proportion and as percentages and have one of them be correct and one of them be incorrect. So at least there's no worry about that. But a very quick procedure, and since we already know how to do confidence intervals, it actually came up real quickly for us. Okay, we're going to do another one of these. Let me put another problem up here for us. So let's, I don't know why that keeps coming up. Let's move that out of the way. Well, that got awfully big quickly. I'm going to go back to my original size. Let's say it's about there. All right, let's just move that out of the way because I'm going to pull up another problem. We'll put it right there. So let's go in. The next problem is 1252. And these problems are always kind of fun because you get to, how about that? We've got these in order. So let's see. So, oh, I just want to copy. Copy. And then we'll go back to my worksheet and we'll paste it right here. That was easy enough. Drinking habits, let's make that a little bit bigger. Okay. In a nationwide survey conducted by Pulse Opinion Research LLC for Rasmussen reports, 1,000 American adults were asked, among other things, whether they drink alcoholic beverages at least once a week. 38% said yes. Determine and interpret a 95% confidence interval for the proportion P of all American adults who drink alcoholic beverages at least once a week. Now, notice in this problem, a couple things I want to point out. One is not as good as I had hoped, but the other is going to be okay. So we've got, oops, let's go to blue. We've got that 1,000 adults. Again, that's going to be my N. That's my sample size. We've got this 38%. That's my sample proportion. P hat is 38%, or we would often write it as 0.38 as a proportion as opposed to a percentage. So that's what we have this time. And we want to do a 95% confidence interval. All right. So let me jot those down. So we've got 1,000 We've got 38% and we want a 95% confidence interval. All right, so let's go ahead and do that. So let's jump over there. Let me move this in case that line is in your way and you can't see what I did. So this number came here, and then the 38% was our population, or our sample, excuse me, proportion. Okay, so let's go ahead and do our confidence interval. Now notice 1,000 people. If we wanted to find what X is just N times P. Now we've done problems like that before where we said, hey, I want to find out how many people said that. And if I just multiply the percentage times the number of people total that we asked, that's going to give us the number. It comes from, we'll make that a P hat. If P hat is X over N, and I multiply both sides by N times N times N, those cancel out and I get X equals N times P hat. Well, that's what we're saying here. So notice in this regard, my X value is N, 1,000, times P hat, which is 0.38. Well, that 1,000 makes it real easy. We just move the decimal 3 places. So my X was 380 people. That's important because we need to know what X is when we input it. The calculator can calculate that. We can tell it to calculate that. But you have to remember that it's N times P hat will give you that value. Okay, so let's go ahead and go from there. Again, we're doing a 1 prop Z interval. And since we have 380 people said yes, that's at least 5, so we're good. We also had 620 said no. That's the rest to get us up to 1,000. So we have at least 5 there, so we're perfectly okay. Okay. When we go in, let's just go to the calculator and do it. So let's go over, we'll pull the calculator back up. There it is. We're going to do the same thing. Now notice this time when I go stats test, since it's not on this first screen, I'm going to arrow up and come up to it from the bottom because I see it right there as A. That didn't save me much time because it's almost right in the middle. But there's some other ones here. So 1 prop Z interval. But there's some other of these down here that we haven't seen that we will be seeing as we go on through the semester. Okay, so I have my 1 prop Z interval. This time X, now remember they didn't tell us, they just told us it was 38%. We can have it calculate it for us. We can say, oh, it was the 1,000 times 0.38. And it calculates the 380 for us. Now, here's where you need to be careful. If that came up as a decimal number, the calculator is going to give you an error. You can't put in, it knows you can't talk to people and get a decimal number of errors, a number of people. It has to be a whole number. So if that came up, if you did the calculation and that was 380.2, you're going to have to manually change it to 380. Otherwise, you'll get an error. So do be careful about that. And this was 1,000. Now, here's what I mean by that. Suppose this number up here, suppose it was still the 38%. So I put 0.38, but maybe it was times 1,010 like our last problem was. Now if I do it, I get 383.3. And if I change this to a 95% confidence interval and I go to calculate, it's going to give me an error because that's not a whole number. Oh, error domain, quit. And it gives you an error because X has to be a whole number. So let's quit. We'll go back in there and we'll change it. We'll change it actually to the correct number. But we would just round correctly. If it's a 0.5 or more, we round up to the next one. If it's a 0.4 or lower, we round down. We just keep the number. We just drop the decimal. Okay. So stats, tests, I'll go this way again, right there. I'll choose that. We remember that we had 380. Again, it was 0.38 times 1,000 if you want to do that. So we had 380 out of 1,000. Confidence level is 95. We'll just go down and calculate. And I get, so let's go to 3 decimal places this time. because if I want to change it to a percentage, that works out really well. So it's 0.349. I look at the next number that also a 9, so I have to round up that 9 to a 10. Well, that makes it, instead of 3.4, it makes it 3.50. So my confidence interval is 0.350 to 0.410. Notice population, sample proportion p hat 0.38. Well, that's what we had been given, so we know that the x and the n that we put in were obviously correct. All right, so let's go back and write it up. So we're here, and we're going to say, well, let's put down the interval first, 0.350 to 0.410. We can be 95% confident that, let's see, the determine and interpret 95% confidence for the proportion of all Americans. The proportion of all Americans. Remember, it's all, it's not just the sample. We know the sample was exactly 38%. We're trying to do the proportion of all US adults. Yes, this is American. I think they mean US. So the proportion of all American adults who drink alcohol at least once a week is between, this would probably be a good one to leave as a percentage because they gave us the 38%. But they said, find the proportion. So we'll leave it as a proportion, is between 0.350 and 0.410. And there's our conclusion. You can make that as 0.350 if you want to show off that, hey, there's a decimal there. So notice as a percentage, it'd be 35 to 41%. All right, so that's the idea. We've done some nice confidence interval stuff. And then our next problem, they're gonna ask us a continuation on that. So we'll leave that there because that'll be real nice. Let me pull, ooh, there's a formula I want to show you. Well, let's do this. This next problem has a part A and B. The part A is built off what we just did. The part B, there's a formula for. So let me do the part A and then I'll show you the formula and then we'll do the part B. Okay. I've made an executive decision. That's what we're going to do. All right. So I don't want that. Okay. So let's 1260. It should just be the next problem in here. If I just hit the arrow over, 1260, copy, and we'll go back and put it in. And paste. Okay. So notice it says refer back to the problem we just did, 1252. A says find the margin of error for the estimate of P. So on A, remember margin of error is half the confidence interval. Okay, because remember the way the confidence interval is built, we're going to start with P hat, and then we're going to go over here, P hat plus the margin of error. That's going to be my right-hand side. But we're going to go this way, P hat minus the margin of error. That's going to be my left-hand side. So my interval is actually P hat minus E to P hat plus E. But the idea is this distance is E. And this distance is also E. So we have 2E. So if I find how wide that confidence interval is, and then divide by 2, I'll get E all by itself. So E is actually, in this case, it's the width of the confidence interval Let's move this up a little bit. Width of confidence interval divided by 2. So the width of the confidence interval, we just have to subtract those two numbers. So we got 0.410 and 0.350. So 0.410 minus 0.350 divided by 2, well, that's going to give me a margin of error. Well, 35 to 41% is 6%, so it's 0.06 divided by 2, or it's exactly 0.03, or if we wanted to, we could call that 3%. And so you'll hear things, especially as the political elections and voting on propositions comes up, you'll hear them say things like, oh, for this proposition, we did a sample and 45% of the people we surveyed are planning on voting yes, with a margin of error of 3%, telling you what p hat is. They're telling you what the sample proportion was, but they know they don't know exactly what it is. So they get it to be within a certain percentage. And in this case, they say, oh, let's get it within 3%, or at least it was within 3% to find this 95% confidence interval. Okay, so now for this next part on B, it says, this time find a sample size that will ensure margin of error of at most 2% or 0.02 for a 95% confidence interval. Notice the confidence interval we just found had a margin of error of 3%. And remember, the sample size was 1,000. Now the problem's saying, hey, you know what? If I want to shrink that down to a 2% margin of error, what do I need to increase the sample size to? Because remember, as you get a bigger sample size, you're typically going to be closer and closer to what the actual population proportion is, because your sample size is approaching the population size. Okay, so I'm going to show you that formula, and then we'll do part B. And I think the formula, I just took a screenshot out of the book. I think it'll fit right here into this area. So hopefully it will. We'll see. I'll put that right there. We have to go find it. It's not the very next one because it was putting things in order this way here. Ooh, it's probably not going to fit. We'll see. Let's see. Copy. Here, let's see how small it gives it to us. Paste. Oh, perfect. Okay. So now I wanted to put this in because there's a lot of verbiage in here, but we'll go over it and talk about what they're meaning. So this is to find the sample size to estimate the population proportion P. And it says at a 1 minus alpha level of confidence. So remember, if we've got a 95% confidence, alpha is 5%. It's the probability that we're wrong, making a type 1 error. So that 1 minus alpha is just like saying at a 95% confidence interval. It would just be that alpha in that case is 5%. For a population proportion that has a margin of error at most E, can be obtained by choosing, and then they give us this first formula where they say, let's see, I want a nice color here. Well, I'll do blue, although this thing is kind of blue. So if I look here, that's my formula. If I have no idea, I have to estimate what the population proportion is. If I don't know, I just do 0.25 times z of alpha over 2 over e quantity squared. And that z of alpha over 2, that's the same z of alpha over 2 we did before for sample size. And again, notice it says rounded up to the nearest whole number. So rounded up, not just rounded. So you never round down. These are always round up. It's only sample size. It's only when you're finding n that you always round up. Anything else, we always round to the nearest. But for n, sample size, we always round up. Okay, now if you can make an educated guess of what the actual value is, then there's another formula, this formula right here. You put the guess that you have, it's 30%. So you put 0.3 and then 1 minus 0.3, which is 0.7, which would be the probability of the people. If you have a guess anything away from a guess of 50% is going to decrease what your sample size is. If you don't have a guess, you have to put in 0.5 for each of those, and 0.5 times 0.5 is the 0.25, which was the first formula. That maximizes the sample size. That gives you the biggest sample size to be able to do this. So if you have an educated guess, it will reduce your size. Okay, so let's go ahead and go through this. We're going to use these to answer part B, and notice it says part B, it says obtain a sample size that will ensure a margin of error of at most 0.02 for a 95% confidence interval without making a guess for the observed value of p hat. So I can't use the second one because I don't have a guess for p hat. So I have to use the first formula. So we'll go through that and we'll enter some stuff. So let me just move this up. So for part B, find sample size. And they said with a margin of error of 2%, so that's what E is. So the margin of error is 2%. We still have a 95% confidence level, just meaning we're doing a 95% confidence interval. But this 95% means alpha is 5%. Okay, that's the 100% minus 95%. That's what's left. Or 0.05. Okay, so that's why they have to tell us the confidence interval. That's where we're going to use that. So here's our formula. N is equal to 0.25 times, and what do we have? Z of alpha over 2 over E. Z of alpha over 2 divided by E, quantity squared, and then round up. All right, let's see what we can do. So we have alpha already, it's the 0.05. So when I go through and I do this, remember to find Z of alpha over 2. That's in this case going to be Z of 0.5. That's my alpha divided by 2. And the way we're going to do that, remember, is we use the inverse norm. The value, again, truthfully, is going to be the positive Z value. This is going to give us the negative Z value, but we don't care because we're going to square it. I'll put it in as a negative and then I square it in the calculator and it goes away anyway. But it's inverse norm. And then remember what we do. On mine, it's always areas to the left. So I'm going to have to do the area to the left. So what I'm going to do is I'm going to do that 0.05. That's not a very good 5. 0.05 divided by 2. That's my area to the left. Right here, we won't do that there. We'll do it underneath. Comma. Now, I don't have to put this in unless my calculator makes me, but it's the mean and the standard deviation. Since it's a Z value, the mean is 0, the standard deviation is 1. On a calculator where it's not telling you what to put in, you don't have to put the 0 and the 1 because it's going to default to that if you don't tell it anything else. But that's my area, that's my mean, that's my standard deviation. And that's the mean and standard deviation because this is a Z value. So my Z in this case, we'll call it Z of alpha over 2. Let's go find it. All right. So it's 0.05 over 2. So let's go to the calculator. You guys remember how to do this. We go variables. Inverse normal is 3. Mine walks me through. Oh, my area was 0.05 divided by 2. And you're welcome to just put it in that way. Notice it defaults to mu is 0 and sigma is 1. So we're going to paste that in. If yours asked if it's left, center, or right, mine defaults to left. That's the only thing I can put in my calculator. But if yours gives you that option, actually, if you put in left, you'll get the same negative number as me. The answer is supposed to be on the right side. So if you put right, you'll get the same answer as me, just as a positive, which is really what it's supposed to be. But so I hit enter here. It's going to be negative 1.96 or truthfully positive 1.96. So we go ahead and we put that in. So in our formula, n 0.25, 1.96, and again, if you put the negative, great. That's what it gave me there. Again, this z of alpha over 2 actually means area to the right of alpha over 2, and so it's really not negative, but it's easier to do it that way. My margin of error, remember they told me up here was 0.02. And then I square the whole thing. Yeah, we might as well do that on the calculator since we've been, and we'll do it on the calculator. So back to the calculator we go. Okay. So 0.25 times, you don't have to hit times, you can just put, it's going to go away when we square anyway, divided by the margin of error, which was 0.02 or 2%. And then I square that whole thing. Here's the x squared, that's going to square the whole thing. And that's it, I just hit enter. And I get, now notice this time I didn't even get a decimal. Let's say that was 2401.1. I'd have to round up to 2402. If it was 2401.8, I'd still have to round up to 2402. 101 because there is no decimal. So it's 2401, and that's the answer to the question. So n 2,401. Notice what that means though. When we had a sample size of 1,000, we had a sample size of 1,000 before, and we had a margin of error of 3%. To drop that down to a margin of error of 2%, I have to increase my sample size all the way up to 2,401. And that's when you have to ask yourself, well, how important is it to me to drop that other percentage? And if it's not that important, you say, oh, a sample size of 1,000 is plenty because we'll have a 3% margin of error. But if I want 2%, I have to go up 2.4 times as big as I was before and take a sample of 2,401. Okay, so that's the idea. That's actually the end of this section. So we've seen all this stuff in there, which is nice. That we're doing 3 sections today. That was the majority of the work that we're going to do. Next, we're going to do a hypothesis test on a sample proportion. Let's say using a sample proportion. The hypothesis test is actually on the population proportion. And we're going to look at when we have 2 populations that we're comparing their proportions. So let's jump over here. We'll go to 12.2. Hypothesis test for one population proportion. Excuse me. So we still have most of what we had before. It still has to be a random sample, a simple random sample, and n times 1 minus p, or the x and the n minus x, those both have to be at least 5. So we have to have 5 with and 5 without the characteristic. Okay, so the rest of the hypothesis test is pretty much the same. They give us a new formula for z, but we don't care. We're going to use the calculator. So in here, we're just using 1 prop z test. And so I'm actually just going to jump in and do a problem because there's nothing else really new here. Now, one thing I should tell you, heck, I'll tell you in the next problem. So when we do this problem, so hold out. I'm going to tell you this in just a second. So I'm just going to pull up a problem. So let's put a place here where we're going to put the problem. Let's go back and grab a problem out of here. And the problem was this one, families in poverty. So let's take a look. So 1288. Let's put that in here. Paste. All right. 1288 families in poverty. In 2012, 15.9% of all U.S. families had incomes below the poverty level, as reported by the U.S. Census Bureau. By the way, do your census, fill it out, in American Community Survey. During that 400 randomly Wyoming families, 50 of them had incomes below the poverty level. At the 5% significance level, do the data provide sufficient evidence to conclude that in 2012, the percentages of families with incomes below the poverty level was lower among those living in Wyoming than among all U.S. families? All right, let's highlight a couple things here. First of all, they're telling us 15.9%. That's my population proportion, 0.159. So we're saying in the United States, 15.9% of all families lived below the poverty level. Well, what we're going to do is we're going to look in Wyoming. And in Wyoming, 50 families, that's my X, out of 400 families, that's my N, my sample size, lived below the poverty level in Wyoming. So then the question is the percentage or the proportion of people in Wyoming below the poverty level less than the national average of 15.9%? So let's go ahead and do our hypothesis test. We do everything like we normally do. The only difference is we're not testing a mean this time. We're testing a population proportion. So my null hypothesis is going to be P. Notice it's not mu because we're not testing a mean. It's a proportion, P. And it's not P hat. We're not testing the sample proportion. We're testing the population proportion. So the null hypothesis is that the population proportion in Wyoming is equal to the same 0.159 that it is nationally. The alternative is answering the question, and the question says, is the percentage of families with incomes below the poverty level lower among those in Wyoming? So the population percentage in Wyoming, that's not a lower. The question is that lower than 0.159? And again, you could put those as percentages. They've listed them as percentages. I probably should, but since they're talking about it, well, this one actually said the percentage. Let's change those to percentages then. We'll change each of these to 15.9%. All right. I like percentages better. All right. So there's my null and alternative hypothesis. Okay, so let's go from there. Now, again, we're doing a one prop Z test. We're just going to enter the stuff. Oops. One prop Z test. All right. So remember, we had 50 and 400 and then 15.9%. All right. I'm jotting that down just to make sure I don't forget. And then we've got the 5% level of significance, which we'll look at in a second. So let's flip over to the calculator, enter everything in. Stats tests, but this time it's a one prop Z test. Notice that's down at number 5. So it's down at number 5. There it is, one prop Z test. Again, I arrowed down so you could see which one I'm picking, but if you just push the number 5, it'll just select it for you. You don't have to arrow down at all to get there. Okay, so P sub 0, that's my assumed population proportion. And I'm assuming it's the same as the national average of 0.159. My X, there were 50 people out of 400, that's N, that were living below the poverty level in Wyoming. I want to know if it's a less than, so let's make sure we choose the correct one. So we're saying, oh, we think our population of Wyoming residents is less than the national average of 15.9%. So let's go calculate and see. So we get a Z value. I'll mark down the Z because they usually ask for that on the homework and on the exams. So we've got that that z equals negative 0.186. My p-value is 0.031. And notice p hat, this was the other thing I was going to tell you about, 0.125. Remember we talked about when we started doing hypothesis testing and confidence intervals, and we talked about instead of a confidence interval, we talked about a point estimate. P hat is another point estimate. So P hat is a point estimate of, it's a single value representing the population number. If you said to me, what's your best guess on what the proportion of Wyoming residents are that are below the poverty level? And you can only give me one number. I would say, oh, I'm guessing the probability or the proportions 0.125 or 12.5%. And if I did a confidence interval, it would be surrounding that 12.5%. But P hat is a point estimate, just like X bar was a point estimate. Okay, again, a single number from the sample used to represent a population number. Okay, so that was the third point estimate we've seen, because we had X bar for the mean, we had S for to estimate the population sample deviation. The population standard deviation, and then we have P hat to estimate the population proportion. Okay, so let's flip back through. I jotted those numbers down, and we'll finish our hypothesis test. So again, they told us Z, negative 1.86. My P, let's do this so we have plenty of room. My p-value came out as 0.0, because now P represents the population proportion. P hat sample proportion, but p-value, the probability that I would get my results from my sample if the population was really what the null hypothesis is assuming it is. So that p-value I compare to, let's see, what does it say, at the 5% level. So there's alpha. Again, if you need to change those two percentages, move the decimals 2 places. Is 3.1% less than or equal to 5%? Yes, absolutely. So I see that it is, so I can reject the null hypothesis. And so I go with the alternative that says, yes, it does appear the proportion of all Wyoming residents that live below the poverty level is less than 15.9%. So let's word that. I'll use a whole line here. Yes, it does appear that, and I'll shorthand it, percentage of Wyoming residents that live below poverty level and this is percentage of all Wyoming residents that live below poverty level, is less than, I will say the US, is less than the US percentage of, what do we have? 15.9%. Yes, it does appear that the percentage of all Wyoming residents that live below poverty level is less than the US percentage of 15.9%. So there is our conclusion. All right. And so the hypothesis test in this section, very similar to what we've been doing. I'm only going to do one example because as you see, there's not a lot different going on than what we've done before. Okay, so with that, I'm going to jump into 12.3. We'll do an example there. Let me show you what it's titled. 12.3 is inferences for 2 population proportions. So here we're doing both hypothesis test and confidence intervals. But the only difference is now we have 2 populations. Okay, so we'll say for 2 populations, So for the confidence interval, it's just called a 2-prop Z interval. And for a hypothesis test, you've probably already guessed this, it's called a 2-prop Z test. That's the end of the lecture on this section. I'll show you an example so that you see it really is as simple as that. But make sure you can determine when you're reading a problem, is it just a regular 1 population proportion, or is it a 2 population proportion? Remember that last problem we did with the Wyoming residents? That was a single population proportion because we only had 1 sample and we were comparing it to the US number, but we didn't have a sample of the US. We had that population proportion. In this case, we won't have the population proportion for either. We'll have 2 samples and we're comparing the 2 samples. So let's jump in and do one of these. And what I've picked out in 12.3 is, let's see if I can find it. There we go. What I'm going to do is I'm going to do a problem that has both a hypothesis test and a confidence interval in the same problem. So we'll be able to do both. And so let's see. I'm looking in the book, figuring out which one to choose, but I've already copied it down. So there's no choice. I don't have a choice. I need to go to whatever this problem is, body mass index. There's the one I chose. So let's copy that. We'll paste that into our worksheet. So let's see, about here. There we go. All right. So here's our problem. 12.111, body mass index. Body mass index, or BMI, is a measure of body fat based on height and weight. According to the document Dietary Guidelines for Americans, published by the U.S. Department of Agriculture and the U.S. Department of Health and Human Services, for adults, a BMI of greater than 25 indicates an above healthy weight, i.e. overweight or obese. Of 750 selected adults whose highest degree is a bachelor's, 386 have an above healthy weight. And of 500 randomly selected adults with a graduate degree, 237 have an above healthy weight. So notice there's 2 separate samples. We've got this first sample, 386 out of 750, but then we've got a second sample, 237 out of 500. So 2 samples, so we're comparing 2 populations. All right, that's how I know it's a 2-prop Z test and not just a regular 1-prop Z test. Okay, so now part A, and I kind of wrote over it. So we'll erase that. A says what assumptions are required for using the 2 proportions Z test here. Well, the assumptions we make is that these are simple random samples and that we have either normally distributed proportions or we have large enough sample sizes. Well, we definitely have large enough sample sizes because we had 386 were above the recommended BMI of 25 out of 750. So 386 were above, and we had, over 300 were below. So they only have to be 5. So we're definitely safe there. The other one's easier to figure out. We had 237 that were above, so the other 263 were below. So again, they just have to be above 5 for each of those 4, and they all are. So I'm not going to write that out. We said that should be enough. It's enough for me anyway. Okay, so B, apply the 2 proportion Z test to determine at the 5% significance level whether the percentage of adults who have an above healthy weight is greater for those whose highest degree is a bachelor's than for those with a graduate degree. So bachelors, let's do this. If they have a bachelor's, that's going to be population 1, since that's the first one they told me. And then we'll do a graduate degree, that'll be population 2, because that's the second one they told me. And that's the order they gave them to us up there anyway. So let's do our hypothesis test. So similar to when we're comparing two population means, the null hypothesis is that P sub 1, so the population proportion for the first proportion, is for the first population is the same as the population proportion for the second population. And the alternative, when I've got P1 and P2, well, let's read whether the percentage of adults with an above healthy weight is greater for those with bachelors. So the greater than is going to go that way. Bachelors is greater than the people with the masters. Okay. I said masters. It's any graduate degree apparently. So master's, PhD, whatever it is that you have that's above a bachelor's, if you do have such a thing. Okay. So there's my null and alternative hypotheses. Again, it's going to be a 2-prop Z test. And so let's go run this. Again, I need to jot these numbers down for myself. So we had 386 out of 750. And we had 237 out of 500. All right. We're doing a 5%. Okay. Let's jump to the calculator. We'll input all that stuff in. And we just go stats tests as normal. 2-prop Z test. That's down at number 6. Okay, so let's go ahead and run this. And let's see what we get. Let's see, hit enter. Let me go ahead and put everything in. So X1, and be careful. Sometimes I'll see what people do because they said out of 750 people, 386 were obese. That's in the wrong order. N has to be bigger than X. So if you do something like that, that X was the number of people that have the characteristic being obese in this case. And N is the sample size. So those are backwards. If you put them in that way, you'll get a domain error. So make sure you don't. Let me show you. If I go down here, and we'll just put one of these in, say this was 9, that was 78, just to see what happens. So if I do that, look, I've got a domain error. And so if you get this error and you're thinking, what in the world did I do? Well, you might have put X and N in the wrong order. So let's go stats. I have to hit enter. So I go stats test. Now remember, it's a 2-samp t-test. I'm just going to hit the number 4 instead of arrowing down. It says 2-samp t-test. I don't have the data. I don't have a 2-samp t-test. Stat test. I have a 2-prop z-test. It's number 6. Sorry about that. So X1 was 386. N1 was 750. X2 is 237, and N2 is 500. I'm testing to see if it's less than, so I'm still on the right less than, I believe. I'll have to go check that. We'll calculate this, and let's see. It was a greater than, wasn't it? I can tell it's a greater than because my p-value is so close to 1. So let's go change that. My p-value is actually going to be 1 minus that, but we should do it correctly. I apologize for that. Stats, tests, 2-prop z test is 6. I just need to change this down here to a greater than, because we were saying the people with a bachelor's degree, we're testing to see if their BMI is greater than those with a graduate degree. And so now I get a z value of 1.41 and a p-value of 0.079. The 4 does not round up the 9, even though the number after that's bigger, we don't care. So notice it gave me the sample proportions of each. P hat sub 1, 51.5%, P hat sub 2, 47.4. So we do see there's a difference in the sample proportions, but is that big enough to mean the populations can't have the same proportion? So let's go finish our test and we'll find out. You probably already found out by looking at the other stuff, because the other stuff we need, let's see, they gave us the Z 1.41 and a p-value, this is what we're using to determine, was 0.079, and I'm to see if that's less than or equal to my 5% significance level. And you know what, friends? It is not. That's a 7.9%. That is not less than or equal to 5%. So this time I don't reject the null hypothesis. So we'll say, do not reject the null hypothesis. And rather than writing all those words down, I'm just going to say is not sufficient to show that P1 is greater than P2. And so remember what this was. Our data is not sufficient to show that the percentage or the proportion of people that finish with a bachelor's degree, that their BMI, that there's a higher proportion of those people that are overweight than people with a graduate degree. So having a degree hasn't shown itself, the level of your degree hasn't shown itself to be an indicator, in this case, of whether or not you tend to be more obese. Okay, I'm going to add a step to this. That was actually part B. I don't know if I ever called it a B. We just talked about A. But C, what I want to do is let's do a 95% confidence interval. All right, so let's do that. We already have all the numbers in there. So when I go and I do that, it's just going to be stat tests 2 prop Z interval, which I can't see from there. Let's go backwards. Get it up to there. 2 prop Z interval. So it's down at B. And I've already got all the numbers in there. Let's see. 386 out of 750, 237 out of 500. Now it says a 95, but I said a 90% confidence interval, so we'll change that. And we'll calculate. And I get to 2 decimals, 0.0, we usually go to 3 decimals, don't we? 0.007. So let's see, negative 0.007 and positive 0.088. All right, so let's go do that. And we will say, so it was we did a 2 prop Z interval. And what I got as my answer was negative 0.007 to positive 0.088. And let's see, they gave us percentages. So let's change this to percentages. We can be 90% confident that, and again, always state it in terms of the first population, that people with a bachelor's degree have between, here, let's change this. So that would be negative 0.7% to positive 8.8%. Have between 0.7%, let's not say have, let's say are. Are between 0.7% less likely, well, that's not a likely, less likely, and 8.8% more likely And I think it was to have a BMI above 25. Than those with a graduate degree. But notice I didn't put the negative 0.07%. I said 0.7% less likely and 8.8% more likely to have a BMI above 25. Let's make sure we worded that correctly. And it says what? BMI greater than 25. So there is our conclusion. And notice that's why we couldn't reject the null hypothesis, because 0 is in here someplace. 0 is in that interval. 0 would mean they have the same BMI. Well, if they have the same BMI, then I don't want to reject the null hypothesis. That is the null hypothesis. But if 0's in there, again, then we can't reject it, which we didn't. Okay. Anyway, that's the idea. A lot of stuff in these 3 sections, but we could do it all in one day because they're all related, and we've seen confidence intervals, we've seen hypothesis testing, we've seen finding sample sizes. So all of that we've already done. So anyway, stick with it, do your homework, and we'll talk again on our next live session. All right, best of luck to you, and I will talk to you later.